This is a tutorial on how to create superplots in Prism, specifically Prism version 9.1 on a Mac. The first step is to create a nested table that has the number of subcolumns equal to the number of samples per condition. I have some demo data that I will put in here. You see that we have control condition and drug condition, and then three replicates, three biological replicates, three samples within each. And nested in each sample are many technical replicates, specifically many measurements of different cells. This data in particular is paired in that each day I took one aliquot, split it into two samples, and treated one sample with drug and one sample with control, and then repeated on day 2 and day 3. So I'll call this our nested data. And for a superplot, I'm going to create some summary statistic for each sample by creating a new table, a new column table, and I'll call that summary. And to do that, I'm going to get some information about each sample. In particular, I'm going to find the average for each sample. If I go to analysis and choose column analysis, there's this option for descriptive statistics. And I could choose mean or median as a reasonable summary statistic. In my case, I'm going to choose mean. So within each sample, there are 50 cells that I looked at. And this table just takes the mean value from those 50 cells for sample 1, the mean value for the 50 cells in sample 2, etc. So I can grab these values, the mean values for the control samples, and paste them here. But specifically, I will paste transpose so that they show up in a column. And repeat with the drug values. Paste them in the summary table. And as you see, Prism has already started making a plot of these. Now I'm going to change the plot slightly in that I don't want this line to be median, I'd like it to be mean. And I could have error bars. I could show, for instance, the confidence intervals or the standard error, the mean of these 3 summary data points. Either of those make sense. I think that standard deviation or range don't make as much sense because those error bars are descriptive. They give some information about the distribution or range of the data points. But in this case, we're showing all 3 data points for each condition. So there's no reason to show standard deviation or range. In my case, I'm just not going to show any error bars for the summary stats. Now I'm going to create a new data table, again column, for the combined data. I'm going to call that combined, and maybe put B-swarm in there so I remember that that's what the figure is going to show. And the simplest way to do that is to copy, for instance, the control data over. But now in this combined plot table, I want all the cell level data from each condition combined into one column. So I'll copy and paste those over. Probably would have been better to cut and paste, but then repeat for the drug data. And I'm leaving a space between each biological replicate here so I know where one ends and one the next begins. Okay, now I can create a B-swarm plot, or some other plot that gives some information about all the cell level data. For instance, I could choose a violin plot, and that gives the total distribution of all the values of each cell level data. But in this tutorial, I'm going to choose B-swarm and not show any error bar or average. And now I have that. To start combining the two or superimposing the two, in Prism you can create a new layout. Choose a single pane. Actually, just delete that pane and drag the summary plot and the B-swarm plot side by side. And make sure that the axes are the same. So the summary data only goes to 50. We need to change that. Sorry. Change that to 60. And we have to make sure that these two plots have the same width and height. Because I chose the default, they are. But if we did want to change them, you could go to the original data and go to, for instance, the frame and origin, change the width and height, or under the graph settings, if you added a different buffer between each column, make sure that those are the same for both plots. Now, I'm going to use the averages plot as the sort of baseline plot. So I will make this have the axes labels that I want. If I want to make these bigger or bolder, now would be the time. But for now, I'll leave it like that. I do know already that I'm going to want these dots bigger, and I can see that by going to my layout, and I can overlay these two. Now you see when you overlay them, you do get some shadowing. That's easily fixed by just coming to the B-swarm plot, deleting these labels, and going to the frame and origin option, and just hiding both X and Y axes. And you can make this disappear by changing the transparency to 0. Don't delete that, or it changes the width of the plot. Okay, anytime you make a change to one of the plots, make sure they're still overlaid. Best way to do that is drag one on top of the other, and when the axes align, you'll see the little dotted lines, and the plots will pop into place. So these are aligned, and you can already see that the averages dots are going to be too small to really show up. So we can go back to the summary data, and for all the data on the graph, I'm going to change the size and the style, and I'm going to change the line so that pops out too. Now those are a little more obvious. We can make them more obvious by color coding. The way to color code in Prism is to go back to the original data table, highlight the data you want to change color, and go up to here to this change function. Change the color and the symbol color in the linked plot. Here I'll make these magenta, and these data points I'll make green. Middle ones I'll make gray. Each time you select a different data set, you have to come back to this change option. Now that we do those, you can see that they're color-coded. I also see that I'd like to send the bee swarm to the back. So under range, you can send to back. Now I could leave it like this, where I have color coding, and because I did want to display some pairing, because as I said before, day 1, these two came from the same aliquot, and you can see from the plotting that I've color coded those the same. So now you can see that day 1 was generally higher across the board than day 2 or day 3, and that pairing helps communicate the linkage between these. The color coding communicates the linkage between these data sets. So this here is a superplot. It has the information about all the cell level data. It could be a violin plot, but we've chosen a bee swarm plot. And superimposed on that is summary statistics about each sample. We could further color code the plot by going to the bee swarm table, again highlighting each replicate. That's why I put this space in here, and color code those appropriately. We made sample 1 magenta, and we made sample 3 green. So I'll do the same thing for the bee swarm level data, the cell level data. And now we've color coded those. Now if we wanted to add p-values, now we have 3 data sets really to think about. The wrong way is to come back to this combined data set and to treat each cell as if it were an independent test of the hypothesis, an independent experiment. If we were going to do it that wrong way, we'd select all the data and run a t-test. And you see you do get a tiny p-value, off the charts really. But the thing to check for, and the warning sign, is that the degrees of freedom is much higher than the number of samples in our data set. We had 3 samples, but in this t-test, it's assuming 298 degrees of freedom. That is incorrect. A way that avoids false positives and makes more sense is to treat each sample as an independent test. Day 1, we tested the drug by applying the drug to one sample of aliquot and the control to another sample. That's one test. And 1 day of randomizing the samples into the 2 treatments. Day 2, we repeated the experiment and tested the hypothesis again. Day 3, we tested the hypothesis a 3rd time. So we only have 6 samples. I can now do a t-test, or of course I could do an ANOVA or another straightforward statistical test. But in this case, I am going to do a paired design because each of these days, these 2 samples were taken from the same aliquot. So we expect them to be paired. That removes some of the variability. And you see now that our degrees of freedom is 2, less than the number of samples. We had 6 samples, but because they were paired, we only had 3 pairs, and the degrees of freedom is 2. And we get a p-value that is a little more trustworthy. A third way in Prism is to do a nested analysis. To do that, we use this nested sheet, and we can choose a nested t-test, or there are other nested options. The nested t-test takes into account the fact that the cell level measurements are repeated technical replicates within each sample. So you see that the degrees of freedom is less than the total number of samples. It's only 4. It's not 300. The downside of using this nested analysis in Prism is it doesn't allow for paired tests. So you see that we have a false negative here because the power of an unpaired test when you have a block sample design, the power is decreased. So in this case, I'm going to go back to our summary graph and add the p-values in. I like to display the actual p-value that I calculated. A benefit of doing that is that a reader can actually plug in, because we're showing all the data, they can plug in these 6 values into their own software and calculate the same p-value I got. Or they can run a different statistical test if they desire. Now you see we have a superplot. Because we added something to one of the plots, we've modified one of the plots. It's always important to check that the 2 axes are aligned, and now they are. Now we can copy and paste this into Illustrator or another image manipulation software that we'd like to use.